Okay, we are live, and we're starting. This is the first episode in an open research series. And while I wait for people to come in, I'll just introduce that real quick. We're basically doing this series, trying like we really value building in public at Fluent, and like part of that is like researching what to build, and we want to do that in public as well. I think it's one thing that I've certainly admired about the crypto like ethos is that so much of this stuff is actually done on Twitter. So, but one thing that's not usually done on Twitter are conversations like this. So we're gonna try it out, and it's gonna be this whole series is gonna be from the perspective of a roll up team like we are, just thinking through certain design decisions, and looping in the best and brightest in each of the respective categories as we do. So this is the first episode on ZK, proving Plonky 3, SP1, all things like ZK that we're thinking through. And first off, I'm Dino, the assistant cheerleader at Fluent, and then I'm here with the Blend Daddy himself, Dimitri, and our special guest, not a ZK Wiz, but the ZK Wizard, Daniel Luberoff. Thanks for joining us, Daniel.
Yeah, thanks for having me.
Of course. So just to kick it off, I mean, the way we'll do this is I'll pose some. You guys are much more technical than I am, and I will pose some like kind of high level questions more from like the go to market and kind of like product side, and we can just like go down whatever rabbit holes you guys want. Feel free to chime in with like different types of questions. We can keep it open, but I'll just get the conversation started. So the first question I had, or I guess just the way we can kick this off is Daniel, can you just give a high level overview of some of your ZK work that I think most people watching this probably know you for. So Plonky 3 and kind of the family of Plonky technologies, and then maybe you can touch a little bit on SP1 actually, which has been surrounded a lot of our conversations that we've had recently with you and internally, and then just talk about like how these technologies work together.
Yeah, definitely. So this family of Plonky libraries, it started with Plonky 1. That was several years ago now, and that was right around when the Halo paper came out from Sean, Dara, and Jack. And we were trying to use that to implement a very fast recursion scheme. And well, yeah, I won't say too much because it's sort of outdated technology now. But it was okay. It wasn't as fast as we liked. And from that, we switched to focusing on fry-based recursion in Plonky 2, which was, for recursion, it was very good. We made it a few hundred milliseconds to do a recursive proof, but there were some other limitations with Plonky 2 where it just wasn't very flexible. It could do certain things very well and other things not so well. And that was the motivation for Plonky 3 when we really tried to generalize things and build more of a toolkit, almost like ArcWorks, where there's these core APIs and there's lots of different primitives that can be implemented by them. For example, a PCS API, which could be a fry-based PCS or could be pairing-based or something else. And yeah, that's my focus right now is on Plonky 3 and supporting the users of Plonky 3, such as SP1, for example.
So how like for somebody who's less familiar with like how those two technologies work together, like how would you explain it for them?
Yeah, so Plonky 3, I'd say, is kind of a toolkit that you can use to build your own prover. It doesn't really have a end-to-end prover except for a very basic one that doesn't really work for SP1 or a lot of other applications. But it has a lot of useful primitives, things like a fry-based PCS or a CircleStark-based PCS. Um, so somebody like Succinct can take these primitives, kind of mix and match the pieces that make sense for them, and use that to build a custom prover for their needs.
Gotcha. So how about let's kind of like place those technologies within the rest of like the modular stack that a lot of people are probably aware of, at least at a high level right now. There's this term thrown around a lot, which is like VMs, EVM, alt VM, which I think gets bastardized a little bit. And then you hear like ZKVM, and you hear it's like, okay, well, like what's with all these like VMs? And so like, can you explain to the audience how like, for example, like our Fluent like VM or other types of VMs or L2s can work with technologies like SP1 and thus Plunky 3, which is used in SP1. And then, I mean, you can even mention like AgLayer, since you've done a decent amount of course work designing that as well. So yeah, like L2s, VMs, AgLayer, just contextualize Plunky 3 and SP1 for people.
Yeah. So although Plunky 3 is technically more general, it can be used for fixed circuits or whatnot. Really, we see the future for most of ZK as ZK VMs, especially these modern ZK VMs like Velida or SP1, which support conventional code like Rust. And that's also what we're using in the ag layer, because in the ag layer, now that we have these modern tools like SP1 that let us express our application logic in Rust, we preferred that rather than handwriting circuits, which we've done in the past, and it's just a bit more painful. So yeah, although Plunky 3 isn't is more general than that, we like our main users of Plunky 3 are ZKVMs like Velida and SP1.
And then how yeah, I guess how, okay, so like how should people think about um a like execution environment or VM, like like Fluent, or even just like a move VM and SVM, whatever, when people hear that that's using SP1, like what does that actually mean?
Yeah. So I think there's a few ways to do it, which maybe Dimitri might have more insights on. But I think, one thing you can do once you have a ZK RISC-V or something like that, like SP1 or Velida, you can take any interpreter and compile that to, let's say, RISC-V. So that's the approach that, for example, Zeth, right, is taking, where they take Reth and compile it to RISC-V, and that's a very nice approach, because in theory, you can reuse all of the logic of this existing EVM interpreter. Um, but there's also other approaches that are more like transpilation, where you take WASM or EVM or whatever it is, and compile the specific application to whatever the native code of the VM is, whether that's RISC-V or something like Miden assembly or something like that.
Gotcha. And oh, go ahead.
Oh, sorry. Go ahead.
Oh, I thought you were, I didn't want to interrupt you. So okay, Dimitri, let's tie in the Fluent part. How, I know we've been doing a lot of research into SP1. We're thinking about like different ways to, to potentially tie in the technology. How would, can you talk a little bit about the, some of those insights, and maybe even like how we would leverage that tech?
Yeah, sure. So there are, of course, tons of advantages on doing this. So as you know, we worked on our ZKVM, on our blended ZKVM, and if we start to blend, we blend everything, and there is no excuses even for SP1. So we're doing research on how to enable blended execution. Oh, well, let me remind what is blended execution and how it affects the ZK proving process. So blended execution is a concept that we use to represent all state transition functions in a more efficient way. The biggest benefit is we can have almost zero-free transaction execution calls, because there is no need to have any interpreter inside, and we can, as Daniel has recently mentioned, we can literally transpile everything to only one citizen language that we have, and we adjust our VM structure and our execution trace with ZK proving circuits to make sure all processes that happen and all transition functions that we execute inside Fluent happens in the most possible efficient way. And of course, it is not possible to achieve in existing ZK VMs because it requires a lot of modifications to be applied on how you manage execution frames, how you prove nested calls, how you do system interruptions, how you do context switching. And it requires these general purpose ZK VMs to be modified to have these features supported. So we're doing research into SP1 to try to enable blended VM inside SP1 compatible execution traces to make sure that we can do these blended call proofs for apps interoperability using SP1.
Makes sense. Daniel, when we met, like, was a while back now, and I remember the way you would describe like Plonky 3 at the time was in more of like a nascent stage, and I guess things have clearly evolved a lot. So like for people who like us who are considering using some of these technologies, how would you classify like the maturity or phase that they're in? Is it like totally production ready? Like how should roller teams think about it?
Yeah, I would say it's production ready. Of course, we don't provide any kind of warranty or promise that there won't be any bugs, but we have been through one audit that we've addressed the couple of findings that they had there. And yeah, we consider it ready to use. I will say some things are still changing a little bit, like on the API side. So if somebody wanted a very stable library, then this might not be the one. But even then, it's getting more and more stable over time.
Is there like, are there any are there any scenarios where you would shy away from people using it at this stage of maturity, or is it all the same to you? It's like, okay, well, if you're going to use it for like a heavy DeFi like roll up that is supporting $1 trillion worth of capital versus like some like app specific game roll up or whatever, like you kind of get the gist of the question. Are there some scenarios where you're like, it's not quite ready for that?
Yeah, that's a good question. So I would personally, my personal view would be that if it's securing, billions of dollars of value, then there should probably be some kind of backup. Um, but I would have that view for a lot of ZK tools, because things like Plonky 3 or SP1 or a lot of these modern ZK tools just have a lot of code and a lot of pieces, lots of surface area where there could possibly be bugs. And it just takes one bad line of code potentially to ruin the security of the system. So it's definitely scary to. So maybe let's take Zcash as an example. Zcash, by its design, they can't really have any kind of backup security or like a strong backup security. There's nothing like a centralized sequencer who you might trust, who can send check everything and reject any transactions that are invalid. Nothing like that exists in Zcash, right? Because of its privacy model. So Zcash has to be extremely cautious because there is no backup, basically, except for like upgrading to a new version and checking that not too much money went to this new version of Zcash. So for something like that, it's probably best to use something like very mature and really as simple as possible. Like they probably shouldn't be using some ZK code that has 100,000 lines of code because it's just too much surface area. Yeah, that's my take.
You brought up well, you kind of started to answer the question I was about to ask, but maybe we can like take it a step or two further. In terms of like we're in L2, for other L2s thinking about this, like you mentioned this notion of backups. Like what are different types of backups that we should consider?
Yeah. So I think there's a lot of options. One would be using a trusted sequencer. So depending on the type of chain that it is, maybe there can be some one sequencer or some set of 5 sequencers or something like that who people may trust to not include invalid transactions. Uh, the other could be trusted provers. So maybe maybe anyone can sequence a block, but then there's some permissioned proving process in there. But the other could be some kind of multi-layered approach. So that could look like maybe using, for example, 2 different ZK VMs together, and they should be proving functionally the same thing, but we require 2 proofs from both of them. Ideally using entirely separate stacks, like one using Plonky 3, one using Halo 2 or something like that. That could be an option, or even using ZK plus fraud proofs or something like that.
That's interesting. So there's clearly a number of different options. Dimitri, like I know, how do you have any kind of further thoughts based on what he said, like how we want to approach it? And obviously it's like clearly it's early days for rollups doing all of this stuff. Like I can't even, are there any rollups right now that actually have the latter couple of backups that you talked about? Like I feel like maybe there are.
So yeah, I see this more in a long-term perspective. Because in a short term, I think nothing can change significantly. But in the long term, we can reimagine and rethink the entire layer 2 and all this execution layers concept, and think how to fully split and delegate all roles into this execution process to different parties. And it will happen. The biggest bottleneck that prevents this from having this is the performance, of course. And we finally see that there are a lot of projects who are trying to achieve this, who are trying to build this model-like level-based execution system where you split sequencing, storage, backupping, and etc. And you can have a lot of like different ways how you prove correctness of all these operations. And I think this is the future of all execution networks, where you focus on one specific task and you optimize the specific task, because like for market, of course, it's more beneficial and more efficient.
So we might outsource like some of those things.
Yeah. So like it is the future. In the future, I think everyone must outsource this.
Right. I mean, in the near term, I feel like everybody stands up their chains or especially their rollups with like, training wheels, and then like clearly like does that over time. And so like as that develops, I think we're coming into the market at like a pretty interesting time, because like more of those modules will be like maturing with us that we can feel more confident like outsourcing to. Obviously, like the first generation of rollups had to have to do like everything themselves, and then and even at this point in time right now, there aren't really like a lot of those modules that people can trust. Like, some of these rollups that already have like billions of dollars sitting in them, and you have like a new module of the stack that comes to market. It's like, okay, well, are you going to trust that? Like, that's not as nearly as mature as you are, and you built everything in house. So like, it's kind of cool. I think we have this like flexibility over the next few years. So another question that I was going to ask, and I guess this is kind of answered already in a way. I was going to ask like Daniel, over like we're seeing a lot of people adopt Plonky 3 and SP1 and some of the things that make use of Plonky 3. And I was going to ask you like how you see this playing out over like 1 year, 2 years, 5 years. Kind of hard to predict, I guess, beyond that. But like, do you think there are specific use cases that are better for that Plonky 3 is like better for, and other use cases that it's just clearly not? I mean, putting aside the fact that we were just talking about like backups that you might like inherently need to solve that problem with 2 different types of proving systems. Like, but putting that aside for a second, do you see like different ones better for different things, or do you think there becomes kind of like a standard over time?
Yeah, so I would say, Plunky 3 tries to be fairly general and adapting to different use cases, but there are maybe a couple of things that it's not great at. So one would be like GPU provers, which actually there are a couple efforts to accelerate Plunky 3 using GPUs, but it's they're kind of they don't integrate very nicely with the kind of the module system that Plunky 3 has, because it just doesn't have a notion of, oh, this data lives in system memory and this other data lives in video memory, and then here's the pattern of how the data moves around. That it just doesn't have any notion of that. So Plunky 3 works better with actually unified memory systems like Apple chip, for example. The other thing that we haven't supported so far is things like the Binius scheme, and the reason we haven't supported that is because it's really a different programming model. We have this in Plunky 3. We have basically standard APIs for errors, and then we have a bunch of different tools that you can use to prove errors. And Binius can still be used to prove errors, but they're kind of a different type of error where now each register has a different width and whatnot, and we just haven't really figured out a good way to support that in the same set of APIs so far. So I guess to connect that back to your question, if somebody was maybe doing something with a lot of binary data, like say proving tons of Keccak hashes, then it might be best to use a Binius prover instead.
Gotcha. So with like the go-to-market hat on, I want to ask you both like something. So we're starting to get pretty solid interest from like consumer social gaming developers, and people are starting to build those types of apps that need like higher throughput. I like, again, just like pure go-to-market side, like I don't want to price those people out, but at the same time, like we want to make like we are very attracted to like the security properties of like these ZK systems. So I'm curious to get both of your thoughts. Like, how should we just make sure, like, what's the appropriate spot on the trade-off space over the next few years so we don't price out those types of users? Either one of you can take it, but I'm curious how both of you think about it.
So on our side, we have been, we're always working on performance, including cost performance as well as latency. And over the past few weeks, we've actually made a lot of improvements, which have, at least on my laptop, it's given about a 3x speed up or so. So we're always trying to make things faster and cheaper. We're also working with Fabric on basically Plunky 3 prover powered by Fabric trips, which should give between 1 and 2 orders of magnitude speed up there on a cost basis. So yeah, we're always I think these things are improving so quickly, and if we look out another 1 or 2 years, I think the costs will be quite a bit lower even than they are today.
Yeah, no, it's amazing the rate at which this is happening. That's absolutely, and like bravo to all of that. It's incredible. And I guess Dimitri, we've talked a little bit about like like a full ZK system versus starting with like an optimistic ZK system. Do you want to talk a little bit to how we've thought about this?
So yeah, before I want to add to the Daniel's response, the first thing, I think we all know that today the performance is not an issue for blockchains. The biggest issue is decentralization and so-called network boundedness or latency problem, because the time that is required to propagate the block and to check that everything is correct on all parties in the world takes a lot of time, and no matter what VM you use inside, without solving this particular problem, you cannot overtake this. But ZK here is the end game, because it makes centralized system trustless. And the biggest issue we have right now that must be solved in the near future is performance. Why performance is the issue? Because with low performance, the overall cost on supporting the infrastructure for creating proofs is very expensive. That makes the system much more centralized. You must use dedicated servers, dedicated expensive servers that for most of parties quite expensive and hard to keep. And to solve the problem, we need to optimize and achieve as low performance of the proving computation as possible to make the system centralized, so-called semi-centralization, and trustless at the same time. It can help us to scale all existing blockchain solutions by enabling new VMs, by adding new execution environments, by increasing number of transactions per second to be executed, etc. And sorry, what was your question?
No, I was asking. As just we've talked internally about like starting with optimistic ZK or things kind of like.
So, yes. So actually, yes, my answer goes right after my answer. Optimistic ZK is a compromise today because it can help to partially solve the problem to make the ZK enabled for everyone without relying on heavy computations. So it can work for now, but I think that in a meaningful period of time, like in nearby future, the problem must be solved and everyone must go with pure ZK computations. But of course, it can happen with enough acceleration, with more faster memory, with faster proof generation concepts, etc.
Yeah, that's a good point about latency. It's not always cost that's depending on the use case, sometimes latency is more important. I think in the past there hasn't been enough attention on that. There's a few dimensions to that. Like one would be for a ZK VM, what are the real sequential bottlenecks? And usually there's parts of the prover that can be just parallelized basically as much as you want, but then there's other parts that are more sequential, like the actual simulation of the program and whatnot. And there hasn't been too much attention yet on how do we make that sequential part as fast as we can. And there's also questions of like how best to parallelize and things like, for example, if we want really good latency, then maybe we should run a single prover process on a machine with lots of cores rather than breaking it up into many small pieces, and then they all have to be aggregated beyond that, which would add additional latency on top.
Yeah, that's true. Yeah, it can happen if you run some sort of proof computation marketplace where all parties can compute proof. And here, yes, you also have the same problem. But since if the price of the proof computation can be lowered, so in this case, you can even delegate all the computations to the party who initiates the transaction or operation, and it can calculate modification of all your states in advance. And so in this case, you can lower the proof computation price to the transaction propagation time. And in this case, it won't be very expensive.
Just wanted to give you a chance to jump in, Daniel. I wasn't sure if you wanted to add on that.
Actually, just one other thought. Actually, with our partnership with Fabric, the Fabric team has made things like FFTs and hashing extremely efficient on their chips, and there we're really just running into trace generation, or especially like simulating the VM is becoming the bottleneck, because that's not something that's easy to accelerate or massively parallelize.
Yeah. And of course, ordering, yes, because you cannot calculate all proofs and state diffs in advance if there is no deterministic ordering.
That makes sense. Okay, so as far as use cases go, like we're talking about, some of these improvements, and like things are dramatically getting dramatically more efficient, like year after year. But yeah, I feel like every step of the way, there's bound to be like use cases that are right around the corner, whether it's right around the corner, like 1 year, 5 years, 10 years, but just generally looking out, like what are some ZK use cases that are exciting to you both today, but not feasible? Like, what are you most excited about over the next like 1, 5, 10 years, let's say? I mean, this could be anything. It could be like relevance to this like roll up in blockchain conversation we're having, maybe some type of like FHE like use cases, like whatever. Or it could be client side proving. It could be literally not blockchain related at all.
So I think the most exciting is that using ZK, everything we discussed right now, everything you can build with all these sequencers, all these new VMs, new execution environments, new rollups, new dedicated applications, hidden computations, HEC computations, all this happened because of ZK. And yes, we haven't achieved the significant performance of ZK yet, and it's still the bottleneck, but we already have achieved a lot of progress in designing such solutions and inventing something new that can be used in blockchain and make it more efficient and more adoptable by users. So yeah, I think everything that you can build on the top of these new technologies is a game changer.
Yeah. For me, I'd say, I'm really excited about things like ZK RISC-Vs or other things like Valida in that category. And that's maybe it's more of the present now than the future, where it's already starting to become very practical for certain things, where you can just take your Rust code and compile that to some ZKVM and prove that. But yeah, for me, that's the really exciting thing, just being able to take, for example, in the future, maybe you can take the RISC-V verifier and compile that to be proven by SP1 or something like that, where once that sort of thing becomes practical, then you can just mix and match without really worrying about efficiency. Or maybe another cool use case would be something like clients, where you just take some normal Rust library for verifying the signatures or the validity proofs of some chain, and without having to rewrite anything, you just run that on some ZKVM.
Yeah, totally agree. Because all these ZKVMs, all these general purpose solutions, they really can let anyone to participate in ZK development without even knowing how it works and how it's constructed under the hood. Yeah.
Mhm.
And of course, yes, one day we will see all these general purpose KVMs, where you can execute it and create proof with no difference on how you do optimizations and the cost. So actually, this is what happens today with a normal programming. You don't care about the performance of your program because you have all these optimizations. Your computer is quite fast. Even if your code base is not very efficient, there is no much performance difference unless you do some really performance requirement task. So it helps to adopt all these regular developers to start contributing into ZK and doing ZK related applications.
Yeah, exactly. And I think when we get to that point where basically performance is solved, besides a few edge cases here and there, then I think things will become sort of boring in a way. Like at some point, you run out of problems to solve, right? And this just becomes a very boring, commoditized technology, a bit like compilers or that sort of thing, where
Yeah.
it won't be exciting anymore. And I think in 10 years, this sort of thing won't be exciting because it'll just be commoditized and like a solved problem.
I was gonna ask, like, in terms of time frame, like when when you say that, like what time frame comes to mind? You're saying like 10 years where this will start, be less interesting in that way. I mean, in a good way, because like it's everywhere.
Yeah, I think we're already almost there, or sort of on the cusp of being at the point where like it's a solved problem and this technology is commoditized. There's several different solutions that meet, for the most part, meet the needs of most applications already. So yeah, I think we're almost there already. There might be, it might take several years for the sort of hotness to die off now that there's this hotness aspect in ZK. But yeah, I think in 5 years or so, this it will be less exciting because the problems have already been solved.
What are the edge cases that come to mind that are that it'll always be chasing? Like is it like AI? Like what comes to mind?
Yeah, yeah, that's definitely one. ZKML is a big one that really pushes the performance limits of ZK schemes. Maybe another one could just be proving some chain like Solana that just has very, very high throughput, and that could be a challenge as well. Um, yeah, and then there might be a few cases where maybe cost isn't an issue, but maybe latency is still a challenge. If, say, there was like a succinct blockchain that wants to have ZK-based light clients and wants them to be able to confirm transactions within a second or so.
It might just be too slow.
Mm-hmm.
The good point you mentioned, Daniel, is you mentioned about Solana. So actually, yes, for ZK it's extremely challenging because it took tens of years for humanity to create some sort of distributed, decentralized computation system with so high throughput and performance. So for ZK, it will be extremely challenging to achieve the same. It also can take from like 10 up to 20 years until we get real-time hardware acceleration for ZK proving. So I think we'll have a lot of exciting tasks to do, even 5 years after.
So, Daniel, you've been very gracious with your time. I want to start to wrap up, but before we do, let's zoom like way out for a second and just say like, why does this stuff matter to both of you guys? Like, why is ZK like important? It could be in the blockchain context. It could be for humanity. Take it however you want.
I need to think about this. My answer is quite simple. I just love computer science and everything that somehow touches computer science. And I love blockchain because blockchain is literally computer science. There is no, these business things like business processes. You don't think about this. You just do your science and you're good with this. And everything you do, like technically, everything you invent, all users, developers, they interact with this directly. So for me, it's very important when something you create, you deliver to your potential contributors instead of, I designed some very optimized database, someone created some non-optimized request, someone created UI backend, etc. And then someone used it as a marketplace. No, it's quite boring. But if you can build something to work with developers, with the industry, I think it's very exciting. It's very interesting.
Yeah, for me, I would say what got me into it initially was the technical challenges. And, but before this, I was working on some pretty boring traditional kind of software engineering work, and was just craving something more challenging. And there's no shortage of challenges here. There's like performance challenges. There's more challenges on the theory or research side, and yeah. But now I would say what the real motivation for me is just trying to fix some of the security problems that we have right now, where for example, like wallets don't, for the most part, don't have any kind of real security. People are just going to websites like Etherscan to confirm their transactions, and when we could be actually using cryptography to show that some transaction was indeed included in the chain, and that the chain is valid.
Totally. No, that makes sense, of course. And yeah, I mean, I think in general, just like this stuff is helping, just like just helping build like much more kind of like robust digital like platforms for people to build on. And like you could either have kind of like more the like the ideological, there's the ideological side of like, you know, permissionless systems and like freedom and self custody and stuff like that. And then there's also like, it's just gonna create better emergent experiences for consumers once you have like this like open state that you can, anybody can build on, and it's more composable and all that. And ZK is like super important for this. Well, cool guys, I guess we can wrap. Thank you so much, Daniel, for coming on, and thanks Dimitri as well. I know you want to do more computer science, and I'm making you stay on Twitter. But yeah, thank you both. Thank you everyone for listening, and yeah, we'll chat later, Daniel.
Sounds good. Yeah, thank you.
Thank you.